Hi everyone, it's Aleem here. In this video, we're going to be looking at an introduction to linear regression using Excel. Let's get started. So far, we've already looked at pivot tables to summarize data, and in example 2.5, we've already looked at how we can plot a line of best fit to make predictions about demand. But simply looking at the sums and averages doesn't always tell us enough about the relationship between variables. To better understand how variables relate to each other, we're going to look at both correlation and regression. Regression analysis is the study of the relationship between variables. There are two potential objectives to regression analysis. One is to better understand how the world operates, and two is to make predictions about the future. And there's different types of analyses that we can do and different types of data we can collect. One type of data we can collect is called cross-sectional data. And these are data gathered from approximately the same period of time from a population. So for example, in class I could ask people, how many of you ate breakfast today? And that would give me an example of cross-sectional data. Time series data involve one or more variables that are observed at several points in time. So for time series data, I could ask someone, how are you feeling today? And then ask them tomorrow, how are you feeling today? And then ask them at different times over the next 5 years, for example, how are you feeling? And this would give me a nice pattern of how they felt over time. One of the things you have to watch out for when using time series data is something called autocorrelation. And this is where time series variables are related to their own past values. Now in every regression study, there is one variable that we're going to call the dependent variable, or other books might call this a response variable or even a target variable. In this course, I will try to use the word dependent variable or response variable. And then you've got multiple other variables called explanatory variables or independent variables. You might see them called predictor variables as well. I typically use either explanatory variables or independent variables when talking about them. You can have many explanatory variables, but only one response variable. If there is a single explanatory variable, then the analysis called If there is only one single explanatory variable, then the analysis you're doing is called simple regression, but if you have many, it's called a multiple regression. The relationship between variables can be a straight line, and that's a linear regression, or you can have curved relationships. And if you have a curved relationship, you can manipulate your data mathematically to give you a linear relationship that you could then analyze. We aren't going to be looking at those in this course. Now your visual system is really good at detecting patterns in data. So a really good way to start analyzing data is just to make a scatter plot between x and y, and this allows you to look at visually whether or not you can detect a pattern. We have already looked at how you graph data using Excel, but be careful, if you're only looking at statistical measures, you might make a mistake. Take a look at something called Anscombe's quartet. Here we've got 4 different sets of data, and I want you to notice the values for x and y in dataset 1, 2, 3, and 4. The mean of x is 9, the variance of x is 11, the mean of y is 7.5, the variance of y is 4.125, and the correlation between x and y in each of the datasets is 0.816. I'll go even further. The linear regression line in each of the datasets is y is equal to 3 plus 0.5x. So all 4 sets of data are identical when examined using simple summary statistics, and you might be tempted to say that these datasets are very similar to each other. But when we actually plot them, take a look at what we see. And just let that sink in. These datasets could not be further from each other. So be very careful. Your visual system is very good at detecting differences in data, but sometimes if you just rely on the statistics, you could be misled. Scatter plots are also very good for identifying what are called outliers, and these are observations that fall outside of the general pattern of the rest of the observations that you observed. Now, if an outlier is clearly not a member of the population of interest, then it's probably best to delete it from your analysis. So for example, if I'm calculating average scores on an exam, and someone doesn't write the exam and therefore scores 0, it really wouldn't make sense to include them in the exam average. If it isn't clear whether outliers are members of the relevant population or not, try running it again with and without them, and if the results you get are practically the same in both cases, then it's probably best just to leave them in. Otherwise, you can maybe report both sets of data with an explanation of why you've included or excluded the outliers. In the example here, we've got the average salaries for all of the employees at our place of work, but the CEO, as you can see, is making a lot more than everyone else compared to years of experience. So here in the x-axis we've got the years of experience, and in the y-axis we've got everyone's salary. And clearly the CEO is making a lot more than everyone else. Now whether you choose to include them or not in your average salary calculation would depend on what it is you're trying to communicate and why. One of the things that's really useful to note is what it looks like when you have no relationship between x and y. And what I mean by that is, regardless of the value of x, you could have really any value in y. Or said another way, there is no relationship between x and y. Here you're just looking for a random plot of noise, where the value of x does not predict the value of y. So for example, if I asked you whether or not you ate waffles for breakfast, that should have no bearing on what temperature it is outside. Correlations. Correlations are indicators of linear relationships, and they're just a numerical summary that measures the strength of a linear relationship between pairs of variables. But correlation does not imply causation, as I'm sure you've probably heard many times. By looking at the sign of correlation, whether it's plus or minus, you can tell whether two variables are positively or negatively related. Unlike covariances, correlations are completely unaffected by the units of measurement. A correlation equal to 0 or near 0 indicates that there's practically no linear relationship, and a correlation can be as small as -1, which is a perfect negative correlation, or as high as +1, which tells you that there's a perfect positive correlation. As I said, correlation does not imply causation, as can be very clearly seen on the next slide. Here's the number of people who have drowned falling into a pool, and how that correlates with the number of movies Nicolas Cage has appeared in. By the way, these come from a really funny website called tylervallian.com. I suggest you take a look. He's got a coffee table book that I think would be hilarious. We've also got the per capita cheese consumption, and how that correlates with the number of people who've died by becoming tangled in their bedsheets. I don't know whether it's more alarming that these things are correlated with each other, or that there's a lot of people who actually die by getting tangled in their bedsheets. Here's the total revenue generated by arcades and how it correlates with the number of computer science doctorates awarded in the United States. Again, these are kind of silly, but it gives you a good reason to remember. Correlation does not equal causation. Now, with a scatterplot or a correlation, you can see that a linear relationship exists. It even tells you the strength of the relationship, but it doesn't quantify them. A simple linear regression quantifies the relationship where there's one single explanatory variable. And what we're going to do is we're going to plot a line of best fit through the scatterplot of the dependent variable y against the explanatory variable x. Here's some terminology you need to know. When fitting a line through a scatterplot, choose the line that makes the vertical distance from the points to the line as small as possible. Now any point on the line is said to be a fitted value, and it's a predicted value of the dependent variable. What I mean by that is, for whatever value of x you choose, a point on the line would be the point that is predicted by that line. In this example here, we've got the dollar amount spent on promotion and how that affects sales. So for any value of x, as x gets bigger, typically we would expect the more you promote, the more your sales would be, and here we do see that there is a positive linear relationship. A point on the line is said to be a fitted value, whereas what you actually observe is said to be an observed value. So I want you to notice this point over here. This is an observed value. The difference between your observed value and the line, and this would be your fitted value on the line, this distance here is said to be a residual, and it's a negative residual in this case because this point lies below the line, whereas these points have positive residuals. The residual is the difference between the actual and the fitted value of the dependent variable, and the fundamental equation of regression says that the observed value is always equal to the fitted value plus the residual, keeping in mind your residual could be positive or negative. Now the best fitting line through the points of a scatter plot is the line with the smallest sum of the squared residuals. And by squaring instead of taking the absolute value, this penalizes you more for bigger deviations away from the line. So if you're 2 units away, that now gives you 4 when you square it, as opposed to just saying plus or minus 2. So the line that we get that again follows this rule is called the least squares line, and it's the line quoted in the regression output or the line of best fit. One of the first things you're going to need to do before we can do any regression in Excel is to install the Analysis Toolpack. To do that, go to File, go to Options, click on Add-ins, and go to Go. Choose the Analysis Toolpack, and then say OK. The first example we're going to look at is example 10.2, overhead costs. The objective of this particular question is to use Excel regression to regress overhead expenses at a company called Bendrix against both machine hours and production runs. We're going to look at whether machine hours on their own, production runs on their own, or even the combined effect of both machine hours and production runs do a good job of explaining the data, that is, the overhead expenses at Bendrix. So we have two potential explanatory variables, machine hours and production runs. Go ahead and open up the overhead costs shell. And what we're trying to determine here is whether or not there's a relationship between machine hours on their own and overhead, production runs on their own and overhead, and finally the two variables taken together and overhead. To do this, we're going to click on Data, click on Data Analysis, choose Regression, and say OK. Our Y range is our overhead. To do this, we can click on overhead, hold Control, hold Shift, and click the down arrow. Our X ranges, and these need to be contiguous, so click on machine hours, hold Shift, click right, hold Control as well now, you're holding Control and Shift at the same time, and click your down arrow. Make sure you choose that you want labels included in this analysis. And what that will do is it will treat the top row as labels. Say OK, and you get your first regression output. Okay, and this is showing you your R squared with both production runs and machine hours included in the analysis. If you wanted to do this with only one of those two variables, data analysis, regression, say OK. So once again, we've got our Y range, which is overhead. Your X range, instead of going from B to C, we could say from B to B. And this would give you your output for machine hours, and say OK. So here's what you should get. Your R squared is 0.3999. Your adjusted R squared is 0.381. And then it tells you that the standard error is $8,584, and the number of observations we have in this dataset is 36. So a couple of things we can get from this. By looking at the R squared, it tells you that machine hours on their own explain 39.9% of the change in overhead, which isn't bad, actually just looking at one variable. The p-value we'll talk about in just a few minutes here, but the p-value for machine hours tells you that there's less than a 5% chance of incorrectly rejecting the null hypothesis. If you don't remember your introductory statistics, the null hypothesis would have assumed that there is no relationship between overhead and machine hours. So if there's less than a 5% chance of incorrectly rejecting that, what we're saying is we have less than a 5% chance of concluding that there is a relationship when there actually isn't. Now, our predicted overhead in this case is going to be calculated by taking the $48,621 that we see over here as our intercept. And to that, we're going to add $34.70 times the number of machine hours. And finally, if we wanted to do this for just production runs, data analysis, regression, say OK. And instead of B, we're going to choose C to C. Our Y range stays the same, we say OK. We get an R squared of 0.27, and that's saying that 27.1% of the change in overhead can be explained by production runs on their own. Here we've got a p-value again. Here again we've got a p-value of less than 5%. Again, that's telling you that the chances of incorrectly rejecting the null hypothesis is less than 5%. So we are comfortable saying that there is a relationship between production runs and overhead. And to calculate or to quantify how much our overhead would be, looking only at production runs, we take $75,605, and to that we're going to add $655.07 per production run. Now, machine hours had a better R squared, and what that's telling you is that the points were more closely surrounding the line of best fit with respect to machine hours than for production runs. But this isn't bad. We're still explaining 27.1% of the change in overhead, looking only at production runs. Standard error. The magnitude of the residuals, remember the residual is the distance between the fitted value and the observed value. The magnitude of the residuals provides a good indication of how useful the regression line is for predicting y values from x values. Now, because there are numerous residuals, it is useful to summarize them with one measure, and that's called the standard error of estimate. It is essentially the standard deviation of the residuals. The smaller it is, the more accurate predictions tend to be. Now, in this course, this is not a stats course, so I don't want you to memorize or manually calculate the standard error, but you should understand that we're happier when it's a smaller number because it minimizes the error that we're going to get if we're using the regression line. Your R-squared is a measure of goodness of fit. It is the percentage of variation of the dependent variable that is explained by the regression, and it is always between 0 and 1. Remember, your R value, which is your correlation coefficient, can go down to -1, but because we're squaring it to get the R-squared is always a positive number between 0 and 1, and the better the linear fit is, the closer the R-squared will be to 1. In a perfect regression, then R-squared would equal 1. So for example, if you went to a restaurant and you ordered a burger and every burger you ordered cost you $3, well then your R-squared between the total amount that you spend at that restaurant and the number of burgers you order will be 1. In simple linear regression, R-squared is the square of the correlation between the dependent variable and the explanatory variable. It is really important that you have a good understanding of what your R-squared is telling you. Now, to obtain improved fits in regression, we can combine several explanatory variables together and include them in the regression equation. Now we're entering what's called the realm of multiple regression. Graphically, you're no longer fitting a line to a set of points. If there's two explanatory variables, you're fitting a plane to the data in three-dimensional space. Again, it's not useful really to visualize this. I think it just makes sense to talk about the fact that with a multiple regression, you have multiple explanatory variables and one response variable. There is a slope term for each of the different explanatory variables in the equation, but the interpretation is somewhat different. The standard error of estimate and the R-squared summary still measure the same things as they were doing before, and you can have many types of explanatory variables that can be included in the regression equation, and we will look at a few of them in this course. Interpretation of regression coefficients. If y is the dependent variable, and x1 through xk are explanatory variables, then a typical multiple regression equation has the form shown below. Your predicted y is equal to a, that's your intercept, plus b1x1 plus b2x2, all the way through to bkxk. The a's and b's in the equation are called your regression coefficients. Each slope coefficient is the expected change in y when this particular x increases by 1 unit and the other x's remain constant. This means that the estimates of the b's depend on which other x's are included in the regression equation. Let's take a look at the same Bendrix example here, but now instead of either using machine hours or production runs, we'll include them both. Now, just a couple of things to note here. Your input y range is D1 to D37. Your input x range is B1 to C37. Make sure again that you check the box for labels. And this is going to allow you to run the regression including both machine hours and production runs as x variables. When you run the regression with both production runs and machine hours included as explanatory variables, we get a much higher R-squared now. What this is saying is that this regression explains 86.6% of the change in overhead. I'm getting that by looking at the R-squared. I also want you to note that our p-values are significantly less than 0.05, right? That's times 10 to the minus 13 and times 10 to the minus 12. So it is highly unlikely that we're going to incorrectly reject the null hypothesis here. And to create an equation that would predict the amount of overhead, we're going to take $3,997, and to that we're going to add $43.54 per machine hour run, plus $883.62 times every production run. Now, if either the slope for machine hours or production runs were equal to 0, then that variable would not add explanatory power. That is, if the slope were 0, then for any value of x, for production runs or machine hours, there would be no change to overhead. Okay, we're at the big green slide. These are some important include or exclude decisions. Now, generally, in this course, the smartest thing to do and the easiest thing to do is just look at your p-value and see if it's less than 0.05, and if it is, we include the value, otherwise we don't. But just some background here. Look at the variable's t-value and the associated p-value. If the p-value is above some accepted significance level like 0.05, then we throw out the variable, or we say that the variable is a candidate for exclusion. We're also going to check whether a variable's t-value is less than 1 or greater than 1. If it's less than 1, then mathematically, we know that the standard error will decrease and adjusted r-squared will increase if this variable is excluded from the equation. Look at your t-values and your p-values rather than correlations when making include or exclude decisions. An explanatory variable can have a really high correlation with the dependent variable, but it could be for other purposes or other reasons. Again, think back to the spurious or the funny correlations I showed you guys earlier, where you could have a very high correlation that really doesn't explain anything. Now, when there's a group of variables that are in some sense logically related to each other, then it's often a good idea to include or exclude all of them at the same time. Finally, just use some common sense. Use economic or physical theory to determine or decide whether or not it makes sense to include variables in your analysis or not.